Hello everybody, welcome into another lesson. So today we are going to talk about functions and their graphs, specifically with the graphs of linear functions. So first we want to talk about, well, what are functions? Functions are a type of relation in which every member of the domain has one and only one member of the range. So the domain is your x variable. It's your input, so it's what you put into the function. It's your independent variable, meaning you could put in anything you want for the value of x, which is in your domain, and you'll get out some value of the range. The range is your y variable, also called the output, because you input something, you get out something. So that's why it's your output. And it's your dependent variable because it depends on what you put in for x. It all depends on that. So a relation is when you have an element of the domain corresponding with at least one element of the range. So here we have three numbers in our domain for our x variable. We have 0, 2, and 4. And then we have our range here, which is our output, our y variable. We see that 0, if you input 0, you get both positive 4 and negative 4 as an output. If you input 2, you get out negative 3 and positive 3 both as your outputs. And if I input 4, I end up getting out negative 1 and positive 1. So this is definitely a relation because each member of the domain corresponds with at least one member of the range. At least one. However, for this to be considered a function is a special type of relation in which each member of the domain corresponds to one and only one member of the range. So this relation is not a function, so this will be considered not a function because each member here has more than one member of the range. So, and if you have, let's say, two of these numbers in the domain had only one member of the range, but even one of them had more than one member of the range, the whole thing would still not be a function because every member of the domain can have one and only one member of the range in order for it to be a function. So this is not a function. So what I am showing you are simple numerical tests to determine if a relation is a function. Alright, so let's input something else here. Let's do it with a couple more examples here of some numerical tests for it. Alright, so in my input, my x, I have negative 5. Whoops, I want to write in black for that. Alright, hold on a minute here. I got negative 5, negative 4, negative 3, then I have 0, then I have 3, 4, and 5. So I have a much more loaded domain this time. What are the values of my range? Let's see, negative 6, negative 4, negative 2, negative 1, -2, -4, and -6. Okay, let me draw these arrows here accordingly. Alright, so we have a relation here where you have certain members of the domain and certain corresponding to certain members of the range. Is this relation a function? Well, if we look at the input -5, it only corresponds to -6 in the range. If we look at -4 in the domain, it only corresponds to -4 in the range. If we look at -3 in the domain, it only corresponds to -2 in the range. If we look at 0 in the domain, it only corresponds to -1 in the range. If we look at +3 in the domain, it only corresponds to -2 in the range. If we look at 4 in the domain, it corresponds to -4 in the range. And if we look at +5 in the domain, it corresponds to -6 in the range. So is this a function? Well, each member of the domain has one and only one value for the range. So yes, this would actually be a function. This relation is in fact a function. Now I'm sure some of you are looking at this like, well, how is that a function? Look over here. You have a couple numbers in the range that have more than one value for the domain. That's completely fine. It can still be a function if a member of the range has more than one value for the domain. That is permissible. You want to worry about if each member of the domain has only one value for the range, and it does. Now later on, when we get into inverse functions, this would still be a function, but this would not be a one-to-one function, because for a function to be one-to-one, each member of the range can have one and only one member of the domain. So, and clearly, each member of the range has more than one answer in the domain, so this would not be one-to-one, but this is a function, nonetheless. Whoops, why am I erasing that? See, I did that too. Hold on a minute here. Going to do one more numerical example, then we're going to move on. Alright, let's do this. I'll just redraw it. I'll redraw the box a little bit here. Alright, what do we got here? We have -2, we have 0, then we have +2. Let's see, we have 1.5, -3.5, 0, 1.5, -3.5. Okay. So we have more members of our domain and range. Now here's how they're going to relate. So -2 corresponds to 1.5 as well as -3.5. 0 only corresponds to 0, and then 2 corresponds to 1.5 and -3.5. So let's look at this relation, okay? We have -2 in the domain, gives you outputs of both 1.5 and -3.5 in the range. 0 in your domain only gives you an output of 0. then positive 2 in your domain also gives you outputs of 1.5 and negative 3.5 in your range. So this would not be a function, because if even one of the members of the domain has more than one member of the range, it's not a function. And two of them have more than one member. Definitely, this is not a function. It'll always be a relation, but it's not a function. Alright, so that's not a function because a couple members of the domain have more than one member of the range. So that's a quick numerical way to tell with a set of data if a relation's a function or not. Now we're going to move on to graphically to determine if something's a function. So I'm going to draw my coordinate plane real quick here. Alright, let's see. Come on down. Get a good representation here. At this moment, I'm not going to worry about numbers and labeling, but we are going to do here what is called the vertical line test, which a lot of you may be familiar with this. I'm sure you are. If you've been with me since pre-algebra or have taken previous courses, you will probably already know the vertical line test, but I'm going to go over it again anyway. So let's say I just give you the graph of a circle, right? So I have the graph of a circle. Is that a function? Well, why or why not? Let's go ahead and do what's called the vertical line test. The vertical line test is a great test for graphs of a relation, and it states that if you take a vertical line and it only passes through one point, it's a function. But if that vertical line passes through more than one point on a graph, it's not a function. So if I can do it in even one spot, that's all it takes. And look, this vertical line passes through this part of the circle and this part of the circle. It intersects at 2 points. It's not a function. So this would not be a function because it fails the vertical line test. Let me just reconnect this a little bit here first. Alright, what's next? What do I want to draw next? Let's say I have here a parabola. A lot of you will probably recognize a parabola from Algebra 1 when we did graphs of quadratic equations. And believe me, they're coming soon again here in Algebra 2. But let's say I do a vertical line test. Really, this curve extends outwards more. I didn't draw it the best, but if you do the vertical line test on a parabola, at least if it's like this, it'll pass. It only intersects the curve at one point. So this would be a function. This is the graph of a function because it passes the vertical line test. Alright, let's say I just have a good old classic line, right? I have the graph, this is a linear function, a normal graph. Well, clearly it's going to pass the vertical line test. It only crosses a line at one point, so that's also a function. That one was pretty easy. I'll do one more for good measure, then we're going to move on again. Now, some of you are probably wondering, is there such a thing as a horizontal line test? And the answer is yes. But that's to determine if a function's one-to-one and is suitable to have an inverse, which we'll cover that at the appropriate time, but that's not today. Now, okay, so what if we had, this is a sideways parabola. What if we had a parabola like that? Would that be a function? Well, take the vertical line test. Notice it passes through 2 points of the parabola, so no, this would not be a function because it fails the vertical line test. It passes through more than 1 point. So the vertical line test is a great test to use on a graph to determine if you have a function. All right, let's just do a few examples here of linear functions. So actually, first, let's talk about a couple things. Let's say, let me plot these here. Let me just plot some points. All right, so let's say for a minute here, we have the graph of y equals 5. So the equation of this line here is y equals 5, right? If it's y equals 5, anybody remember Vux-Hoy? You know what? You could probably hardly see that. In fact, this marker's junk. I'm going to get rid of it. It's just junk, man. Let's say, you know, I'll just write it in black. Y equals 5. Well, who remembers Vux-Hoy? Vux-Hoy, remember the Hoy part, horizontal line, 0 slope, y equals. If you just have y equal to a constant, such as 5 or any other constant, you have a horizontal line. And it would pass the vertical line test if you, of course, took the vertical line. It would only intersect the line at 1 point. But a horizontal line is still a linear function. The idea of a linear function, as the name implies, is you get the graph of a continuous line. That's the idea. Now, let's shift this a little bit here. What if I change this a little bit? And I have, this time, what if I had x equals 5? So what if I had x equals 5? So Vux, vertical line, undefined slope, x equals a constant. So immediately we should be able to see this would fail the vertical line test. It would pass through the entire line. So if it's just x equals a constant, it's not a function at all. So that's something to know about. All right, let's graph a few. Let's talk about linear functions. So, linear functions, as the name implies, would give you the graph of a line. You just think of it like line R, linear. It's got the word line in the name, so the graph will always be a line. Now, examples of that, you have y equals mx plus b. We should remember this. That's the equation of a line in slope-intercept form. Or, instead of y, and really we need to get used to seeing this, f of x equals mx plus b. Since, after all, y is a function of x, this just means function of x. You can literally substitute f of x for y. F of x equals mx plus b. You will get a line. And the thing about linear functions is you always have the highest degree of the equation for the x variable being to the first power. It's always to the first power. The only exception to that is if you have y equal to some constant, which ultimately would be x to the 0 power. If y equals a constant, you get a horizontal line. That's still a linear function. It's implied in the name line. Okay. So let's graph a few functions here. Let's say we have something like, what about y equals x minus 3? We just want to graph y equals x minus 3. Well, in general, it's good to find a couple points and plot them and then connect those dots. As we see, this is definitely a linear function. X is only to the first power. That's the highest degree of the equation. So that's going to be a linear equation. Now, if we should remember right, you should just get a line. You really should only need about 2 to 3 points to graph a line. Now, when we get into graphing quadratic equations or even absolute value equations, which are a little bit later and a couple more lessons from now, you're probably going to need more than 2 to 3 points. But for now, 2 to 3 points should suffice for this. So all you have to do is input something in for x, you should get out a y value. So if I put in x equals 3, that means that y would equal 3 minus 3, which would equal 0. So I would get the point 3, 0, right? So let me plot 3, 0. If I put in x equals 0, of course, I would get y equals 0 minus 3, which would give me negative 3. So the point 0, negative 3 would also be a graph of this. So I think 2 points will suffice. Now you just simply connect your dots and you have a line. And this here would be the graph of y equals x minus 3. Just find about 2 points and you graphed your line. Yeah, so there's that. Now, next lesson's going to be on slopes of lines, which means we will get to talk about the end behavior of linear functions and their graphs. We'll be able to talk about that at that time, which end behavior is going to be a very big topic in this course for functions and their graphs, as well as in pre-calc. And even a little bit in Calc 1 it will be also. But anyway, let's go on to the next one. Let's say all right, let's do y equals negative 5x plus 1. So we'll do the function y equals negative 5x plus 1. Alright, so just pick a point, put it in there. What if we pick when x is 0? Well, that's completely fine. Let's put in 0. So if x is 0, that means y would equal 5 times 0 is 0 plus 1. That would give you a y value of 1. So you would definitely get the point 0, 1 on this graph. That works. We'll get 0, 1. All right, now how about if we have, let's put in something else here. What if I just put in x is 1? I could do that. So if x is 1, that gives me y equals negative 5 times 1 is negative 5 plus 1. Well, that would give me negative 4. So I would have the point 1, negative 4 as a graph also, as a point. So let's plot 1, negative 4, which would be right here. And now I can just draw a dot and connect the, make a nice connection and have a line. And there is my graph of y equals negative 5x plus 1. I think we're pretty good on how to graph lines. We are pretty good on how to graph those. So we're going to look at a few equations here, and we're going to decide whether the function is linear. So first of all, we have the equation, or actually the function, f of x equals x minus 11. So is this function a linear function? Well, how you determine that is take the power of the highest take the highest power of the variable you see. Well, it's 1, so yes, this is a linear function. So yes, we do have it is linear. Now what they would also like to know is, what is f of 4? So let's say we put in f of 4. Well, we should definitely know how to put in values into a function by now. This is why function notation is nice, because then you know what value you're putting in for x. So you just put that 4 in for x, you would get 4 minus 11, which would equal negative 7. So yes, f of 4 would give you negative 7. All right, so what if, yes, here's a good one. F of x equals 2. We just have f of x equals 2. It equals a number. We talked about this not too long ago. So f of x is y, right? That means y equals 2. Hoi, horizontal line, 0 slope, y equals. It's a horizontal line, and if it'll pass the vertical line test because it would only intersect a line at one point. And actually, yes, this is a linear function because the graph gives you a line. So this is also linear. This would also be linear. Now, they want us to find f of negative 4. So put in negative 4 for wherever you see an x. Here's the thing, you don't see an x. You don't see an x. So no matter what value I stick in for f of x, I'm just going to get 2. It's a continuous line through y equals 2. In every direction, no matter what value of x I put in, I'm going to get 2 as my output. So that was a good one. All right, what about, this one they try to trick you a bit. Is this one, f of x equals the absolute value of x minus 5, a linear function? Well, it's definitely a function, but is it linear? And your first thought might be to say yes, well, because the power is to the first power. However, graphically, if you go to graph the absolute value, it's going to look a lot like this on your coordinate plane. That's what the graph of an absolute value function looks like in the coordinate plane. You don't get a straight continuous line going from start to finish or infinity to infinity. So in actuality, this is not a linear function because you don't get a straight continuous line. So this is not linear. And we're going to have a whole lesson on absolute value functions coming up. So this would actually not be linear for that reason. Now, what if we were to evaluate f of -6? So you just put in -6 for x, you'll take the absolute value of -6 minus 5, which the absolute value of -6 is +6, so it would be 6 minus 5, you would get 1. So the answer to f of -6 would be 1. We should definitely know how to input values into functions by now and get outputs. But this is just a brief review. I have about 3 more problems, then we're done. Here's a good one. F of x equals 9x to the third minus x squared plus 2. So we have f of x equals 9x to the third minus x squared plus 2. Is this a linear function? Well, what's the degree of your equation? The degree is always the highest power. The highest power is 3. This is definitely not linear. Not linear at all, because you have a power of 3. Even if you didn't have a power of 3, you still have a power of 2 with that negative x squared, so it's still not a linear function. Not at all. But what if we were asked to find, in this case, f of 2? So let's take f of 2. So just put the 2 in for x. That'd be equal to 9 times 2 to the third power minus the quantity of 2 to the second power plus 2. Well, do your parentheses first. 2 to the third is 8, so this is 9 times 8 minus, all right, what's 2 to the second? That's going to be 4, so minus 4 plus 2. 9 times 8 is 72, minus 4 plus 2, so now just work from left to right. 72 minus 4 is 68, plus 2 is 70. So f of 2 would give you a value of 70 for that. And 2 more problems. Okay, we have f of x equals -2/3 x squared minus x plus 5. Alright, so f of x equals -2/3 x squared minus x plus 5. Is this a linear function? What's the degree of the equation? It's a 2. You have a degree of 2, so this is definitely not linear because you have a degree of 2. So this is not a linear function. It's a function, it's just not linear. It's actually a quadratic function, but we'll get into that later. Now let's say they want you to find f of 6. So let's find f of 6. So you'll take that 6, put it in for wherever you see an x. That'd be -2/3 times the quantity of 6 to the second power minus 6 plus 5. Well, deal with your exponents first. That would give you -2/3 times 36 minus 6 plus 5. All right, so let's multiply the -2/3 times 36. A third of 36 is 12. Take that 12 times -2, you would get -24. So you'd end up with negative 24 minus 6 plus 5. Which addition and subtraction have the same priority, so negative 24 minus 6 is negative 30, plus 5 is negative 25. So you would get a value for f of 6 being negative 25. One more problem, then we're done for the day. What if we had f of x equals negative 3 plus 4x? So f of x equals negative 3 plus 4x. Is this a linear function? Well, look at the highest degree in your equation. The highest degree is 1, so yes, this is actually a linear function. This is linear. They don't always put the powers in order. A lot of the times it should go in descending order. This time they're putting it in ascending order. It's not wrong either way. This is the same as f of x equals 4x minus 3. They just chose to do it negative 3 plus 4x. It means the same thing. But this is a linear function since the highest degree is 1. Now, of course, they're going to ask us to put in... They aren't going to let you off easy, though. What is f of negative 1/2? F of negative 1/2. So put in negative 1/2 wherever you see x. So that would be negative 3 plus 4 times negative 1/2. Well, what is 4 times negative 1/2? That's negative 2. So you'd end up with negative 3 minus 2, which would end up giving you a value of negative 5 for the function. So that's it for the introduction to functions and their graphs, especially with linear functions. On the very next lesson, we are going to talk about slopes and rates of change and the end behavior of linear functions. So I hope everyone has a great day. Take care.